Chapter 5, Rational Functions. A rational function is a function that is defined as f of x is equal to g of x over h of x. In other words, it's one polynomial function divided by another polynomial function. Some examples of rational functions may be f of x equal to x squared plus 3 over x plus 5. We're going to start off, though, by looking at the simplest type of rational function, which is the reciprocal function. The reciprocal function. Reciprocal function is defined as f of x is equal to k over x, where k, that should be a k there, is simply a constant. Now, why do we call that a reciprocal function? Remember that if I have a number like 3, the reciprocal of 3 is whatever is multiplied times 3 to equal 1, which in this case would be 1/3. So 3 times 1/3 is equal to 1, so I say that 3 and 1/3 are reciprocals. If I have a fraction like 2/5, then I would want the numbers that I would multiply to get 1 as my answer. So I would use 5/2, simply inverting the numerator and denominator, because that would give me 10 over 10, which is 1. So what I would like for you to do is find the reciprocal of 2/3 and then prove to me that it actually are reciprocals. And I would also like for you to find the reciprocal of x plus 1 over x minus 1. And once again, prove to me that they are reciprocals. So you'll need to pause the video now and work those two. Okay, hopefully you found that the reciprocal of 2/3 is 3/2, because when I multiply those together, I get 6 over 6, which is 1. The reciprocal of x plus 1 over x minus 1 is x minus 1 over x plus 1. When I use the FOIL method to get those, I get x squared minus 1 over x squared minus 1, which of course is equal to the number 1. So now let's go back to the reciprocal function. Remember, I said it is a function where f of x is equal to k over x, where k is simply a constant. So what I would like for you to do is to punch in your graphic display calculator the following functions: y1 equal to 1 over x, y2 equal to 2 over x, y3 equal to 3 over x, and y4 equal to 4 over x. And I'd like for you to graph those and then look at the graph and notice a few things about them. So punch those into your calculator real quick and then start the video back up. Okay, if I punch in y1 equals 1 over x, y2 2 over x, y3 3 over x, and y4 is 4 over x, and hit graph, notice what happens. All of the graphs look a little bit similar, except they are moved away from the origin when it is the number or the constant term gets larger. All of these are known as hyperbolas. A hyperbola is the graph of the reciprocal function. Notice that there were two parts of the graph. There was a part that was in the first quadrant and a part that was in the third quadrant. I also want you to notice that they don't actually cross either the x-axis or the y-axis. What we say when we're talking about that is that as x approaches infinity, meaning my x value gets larger and larger, so in this case we go from 1 over 1 to 1 over 2 to 1 over 3, and as we're approaching infinity, that's like 1 over 1,000,000. You know, that's a very, very small number. It's getting closer and closer to 0. F of x is going to approach 0, but it will never actually hit 0. So when I look at my graphs there, as my x value get larger and larger out here, the y values get closer and closer to being 0. Also, I want you to notice that as x approaches negative infinity, that f of x also approaches 0. Also, when we look at the graph, our x values approaching 0. As x approaches 0 from the right, put a little plus sign down there to show that we're coming in from the right side, that my f of x seems to get bigger and bigger and approach infinity itself. See, as I'm moving in from the right, positive values of x getting closer and closer to 0, my graph is going up and up, higher and higher, so it's approaching infinity. And as x approaches 0 from the left side, you'll notice that f of x goes to negative infinity. So that's some of the properties of the reciprocal function. What it means is that we have vertical asymptotes is x equals 0 and a horizontal asymptote that is y equals 0. So if I'm going to graph that, I know that over here it'll never hit the y-axis. It'll be an asymptote there. It'll swing around and be an asymptote at the x-axis, and that's also true on this side. Closer and closer to 0 on both the x and y-axis, but never actually hitting them. We call those the asymptotes at x equals 0 and y equals 0. Remember, x equals 0 will be vertical asymptote, and y equals 0 will be a horizontal asymptote. I also want you to go back to your GDC and look at the table of values for here. Let me get back down here where my x is close to 0. Now notice I got a 0 there. I want you to notice that in y1, when x is 1, y is also 1. When in y2, when x is 2, y is 1. In the y3, when x is 3, y is 1. And in the y4, when x is 4, y is 1. So what that tells me is that this graph will always go through K1. And if I look back at that table again, I will also see that when x is 1, each of these is whatever k is. So it also goes through 1k. On the negative side, if I look at that, I will see that when it goes through negative k, it will be negative 1. And when it goes through, when x is negative 1, it'll be negative k. So that will give me 4 points that I can graph in trying to graph one of these. So what I would like you to do now is on a piece of graph paper, I want you to graph y equals 3 over x. So we're going to graph y equals 3 over x on a piece of graph paper. I'm just going to freehand it, but I would really like for you to use a graph paper because I want you to get it exact. So remember what we said. When x is 1, y is going to be 3. And when x is 3, y is going to be 1. And that's going to give us a curve that looks something like this. Also, when x is negative 1, y is going to be negative 3. And when x is negative 3, y is going to be negative 1. So I have the other half of my hyperbola down in the third quadrant. So that is what my graph is going to look like. Now I want you to draw y equals x on your graph. Remember what y equals x is? That is simply a straight line, a 45-degree angle, where the x and y values are the same, so it should go through 1, 1 and negative 1, 1. I want you to reflect the function y equals 3 over x over that line. So if I reflect this point across the line, notice what it comes to. My 1, 3 becomes 3, 1. My negative 1, negative 3 becomes negative 3, negative 1. And that would be true of all of these other points also. What do you notice about that? What I get is when I reflect across, these two sides just seem to change places. Let's look at finding the inverse of this function algebraically. Y equals 3 over x. If I switch places with x and y, and then solve for y, I get yx equals 3. Divide by x, y is 3 over x, and so that is F inverse. Well, notice, it's the same. What we say when this happens is that it is the reciprocal function is a self-inverse function. A self-inverse function. In other words, it is its own inverse. Y equals 3 over x is the inverse of y equals 3 over x, since we reflect across that line. I would also like for you to add in the line y equals negative x, and that is a 45-degree angle coming down through here. And what I would like you to think about is flipping across this line, and what we see is that once again we have the symmetry. It's the same thing on both sides of that line. Notice two separate parts of the graph are reflections across the line. So on a new graph, I want you to graph the function y equals negative 4 over x. And I want you to notice that the negative reflects the graph across the y-axis. So when I have negative 4 over x, when x is negative 4, or when x is 4, y is negative 1. When x is 1, y is negative 4. And it goes through 1, 1. So we have a graph that looks like this. And on the other side, what it does is reflect the two parts across the x-axis. So what we end up with are across the y-axis. You could look at it either way. So what we end up with is our graph in the second and fourth quadrants. Another thing you should know is that the reciprocal functions undergo the same transformations as other functions we've looked at. So if I take the function f of x is equal to 3 over x and transform it into g of x, which is 3 over x plus 2, what happens to our graph? Well, we know that adding 2 out here simply moves it up 2 spaces. What would that do? Well, our vertical asymptote will still be x equals 0, but our horizontal asymptote now becomes y equals 2. And so if we want to graph this function, what we're going to notice is this going to look the same as 3 over x, except that instead of having an asymptote at 0, it's going to have an asymptote at 2. And we'll come right through here.